There are three methods that we're going to use in order to solve systems of equations. The first one is Gauss Elimination, then we have Gauss-Jordan Elimination, and then we can go ahead and use elimination in order to find the inverse of A, and then solve X by saying A inverse times B. So the first one is Gauss Elimination, and with Gauss Elimination we need to use also something called back substitution. So the goal with Gauss Elimination is to perform our elimination steps. So the three that we talked about, multiplying equations by a constant, rearranging our rows or rearranging our equations, and performing our elimination step. We're going to replace a row by adding two rows together. So that's the process of Gauss elimination. We are going to do that until we end up in what's called row echelon form. Essentially, row echelon form, you end up with a lower triangle of zeros, but it's defined by these four characteristics. The pivots are considered the first non-zero entries in your row. If I look at this augmented matrix up here, this would be a pivot, this would be a pivot, and this would be a pivot. Okay, but in row echelon form, the pivots are going to be the first non-zero entries in your rows, and they're going to be in a staircase pattern, something like this. Okay, but that's the definition of a pivot. It's the first non-zero entry. And then below each pivot is a column of zeros. So here, if I look at this pivot here, below it is all zeros. This pivot here, below it is all zeros, and this pivot here, below it is all zeros as well. So essentially what we're going to do is we're going to create a bunch of zeros, where we're going to have a first non-zero entry row and have a bunch of zeros below it. Each pivot lies to the right of the pivot in the row above. So we get this staircase pattern, where each pivot essentially below lies to the left, each pivot above lies to the right. Okay. And we keep going through in that staircase pattern. It's not always a complete staircase. It's not always, I guess, a uniform staircase. Sometimes we don't have an even number of rows and columns, and our REF doesn't have this nice form here. But all of these principles still apply. And lastly, sometimes we end up with what are called zero rows. So rows where it's all zeros, and those come at the bottom. And we will see different examples of what this looks like in our examples on Monday and Tuesday. As a note, there are multiple REF matrices. There are multiple row echelon form matrices for a given system. So for this augmented matrix, I can have different REF matrices depending on what row operations you apply. But as long as we have this lower triangle of zeros here, where each pivot is on top of a column of zeros, and each pivot keeps going that way or this way, then we still have REF. Okay, but there's multiple REF matrices. So for Gauss elimination, the process is going to be this. We're going to write our system equations in augmented matrix form. Here's what this one looks like. And we're going to use our elementary row operations in order to make this a zero, make this a zero, and make this a zero. This is for a 3x3 system. We will look at 4x4s and above as well, where eventually we want to get it into REF form, which is this one. Whatever numbers end up here is going to give us our new system of equations. And then you can see here, this will tell me what my third unknown is. I can use that and plug it into this one to find my second unknown. Use those two to plug it into this one to find my third unknown. That is the process of back substitution. We're going to go ahead and find our last unknown with our last equation, and then work our way up and find all of our unknowns by plugging it into our system of equations. There are some tips and tricks. Tips and tricks are find all the zeros in the first column, and then the second column, and then the third column, etc. And continue that pattern. And we'll go over those tips and tricks in class. The second method is Gauss-Jordan Elimination. And it is the same process as Gauss Elimination, but it takes it a little bit farther from REF into RREF, or Reduced Row Echelon Form. Reduced Row Echelon Form is defined by the following characteristics. All non-zero rows appear last in the matrix, or all zero rows appear last in the matrix. So once again, if we have rows and zeros, they're at the end, just like with REF. All non-zero rows start with the number 1. So if I have numbers with in my rows, the first number is going to be 1. This is what it looks like if it's a nice system of equations with three equations, 3 unknowns. We end up with 1s along the diagonal. But once again, we're not necessarily going to have the same number of rows as columns, so we might end up with some rows with other numbers as long as the first number in the row is 1. When a value of 1 appears in the column, all other elements in that column are 0. So here's a 1, here's zeros. Here's a 1, 0, zeros. Here's a 1, here's zeros. Okay, so all our elements create zeros. Notice, once again, for this nice 3x3, I end up with identity. So essentially, we're trying to get as close to identity as possible, at least on this side, on the A side of our augmented matrix. Okay, and then what happens over here ends up being our solution. So here, this first row easily tells me that the first unknown is this number, the second unknown is this number, third unknown is this number. One thing to note is there are multiple REF matrices for a system. There is only one RREF matrix for a system. And in MATLAB, we can go ahead and find that RREF matrix for a system using the RREF function. You can use the RREF function in MATLAB to go ahead and check your reduced row echelon form of a matrix. Okay, so if we want to go ahead and find the RREF matrix for a system of equations, we can go ahead and follow these processes. So first things first, we write the augmented matrix, just like we do with Gauss elimination. Then we're going to use elementary row operations to transform the augmented matrix into reduced row echelon form. So make this a 0, this is 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 that. Nope, not that one. This is 0. Make this a 1, this a 1, this a 1. Essentially, that's what we're trying to do. Once we do that, then we can go ahead and write our system, or write our solution, because this ends up being our solution. Once again, tips and tricks, eliminate all the numbers in the first column, so find these zeros first, then these zeros, then these zeros. The last method we're going to use is finding the inverse of a matrix, which we can use row operations in order to find the inverse of a matrix. So if I write a system in the form of AX equals B, I can go ahead and know that my solution, X equals A inverse times B. So if I can find A inverse, I can go ahead and do that multiplication, fairly straightforward. So for this process, essentially, we're doing Gauss-Jordan elimination on just A. Instead of attaching A to B, we're going to go ahead and attach A to identity. So in order to find the inverse of a matrix using these methods, we're going to start with A placed next to I. We're going to apply the same process for Gauss-Jordan elimination. Make this a 0, this is 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 0, 1, 1, 1. When we do that, this side ends up being identity, and this side is full of numbers corresponding to A inverse. So now I can go ahead and take this matrix here, multiply it by B in order to get my system equation. So we're going to go over lots of examples on Monday and Tuesday, and I'll show you guys what that algorithm looks like in MATLAB as well.